Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss Newton's method. Newton's method is a method for finding roots of functions, that is, values of x which cause f of x to equal 0. Now the general idea is very geometric, so let's look at a picture. For Newton's method, if here's the graph of a function f and we want to try and find where it crosses the x-axis, one thing we can do is take any starting point, here I'll call it A, and look at the point on the curve a comma f of a and compute the tangent line to the graph at that point. We follow that tangent line back to where it hits the x-axis. Now in general we think of the tangent line as something that approximates the function near the point of tangency, but Newton's brilliant idea was just to go ahead and follow it all the way to the x-axis, even though that may not be close to where the tangent line's approximating the function. Notice this curve is crossing the x-axis back here. And if I were to come up to the curve again and repeat this using that as the point of tangency, I might get something like that, and it would be back here. Now we would follow that procedure again, and hopefully it would get close. Let's look first to see how we find this new point B from our starting point A. Notice the slope of the tangent line is f prime at A, and it passes through the point A comma f of A. So in point slope form, its equation is y equals f of A plus f prime at A times x minus A. Now setting this expression equal to 0 means y equals 0, so that gives us where we cross the x-axis. So B is the solution of 0 equals f of a plus f prime of a times the quantity b minus a. Well, that's very easy to solve. We just move the f of a to the other side. It becomes negative f of a. Then dividing by f prime of a, we have negative f of a over f prime of a, and then shift the a over, and b equals a minus f of a over f prime of a. So that's our general idea. Now let's look at a picture where this will really work. In this situation, what we do is, here's a curve that's more nicely smooth. If I start here at x naught and come up to the point on the curve, draw the tangent line that crosses the x-axis here at x1, and then come back up to the curve, form the tangent line that crosses the x-axis at x2, come up to the curve, form the tangent line, it crosses the x-axis at x3. Well, what we've just found is to get the next point, you take the previous point minus f at the previous point over f prime at the previous point, and that's the next point. So that gives our procedure, the procedure for Newton's method. 1, guess a first approximation to a solution of the equation f of x equals 0. A graph of y equal f of x may help, and of course, in general, you're going to be working possibly crudely, but a rough sketch of the graph may give you a rough idea what to do for a first guess. 2, use the first approximation to get a second, the second to get a third, and so on, using the formula x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. That's provided f prime of xn is not equal to 0. Of course, if this is equal to 0, then this whole expression is undefined. And what does that mean geometrically when f prime is 0? It means that the tangent line is horizontal. Well, if you take a horizontal tangent, that means it's parallel to the x-axis, and so unless the xn was already a root, you're never going to hit the x-axis. So consequently, clearly f prime at xn has to be non-zero. Now in the process of doing this, what you should do is calculate x minus f of x divided by f prime of x. That is, differentiate the function, form the quotient f of x divided by its derivative, put the negative sign and put the x in front. So you form that expression. but then simplify it as much as possible. Then set h of x, say, or any other symbol. In other words, define a new function to be equal to the resulting simplification. So here this h of x you see is a function, and what you're going to be doing is putting a value into the function, computing the value, and then taking the result and putting it back into the function. So we start out with an x sub 0. X sub 1 is h of x sub 0. X sub 2 is h of x sub 1, and so on and so forth. Well, now let's apply Newton's method. Let's take a fourth degree polynomial and find a couple of roots approximated in 2 steps by Newton's method. Here I have f of x equals x to the fourth plus x minus 3 as a polynomial function. And I'm going to use the starting points x naught equal plus 1 and x naught equal negative 1. And in each case, I want to find x2. So we begin by differentiating f of x. F prime of x is equal to 4x cubed plus 1. And so now I'm going to form h of x, which is equal to x minus the original function, which is, of course, x to the fourth plus x minus 3, all divided by the derivative 4x cubed plus 1. Now, let's simplify. So get a common denominator here. I'll cross multiply. So h of x is equal to x times the quantity 4x cubed plus 1 minus the quantity x to the fourth plus x minus 3, all divided by 4x cubed plus 1. And so we'll simplify. H of x will multiply through here. 4x cubed times x is 4x to the fourth. X times 1 is just x. And we'll distribute the negative sign through. We have negative x to the fourth, negative x, and a negative negative 3 is a plus 3, all divided by 4x cubed plus 1. So now we can see our x's are canceling out. 4x to the fourth minus x to the fourth is 3x to the fourth plus 3. So our numerator is simplified considerably. It's just 3x to the fourth plus 3, and our denominator is 4x cubed plus 1. And so that's the function that we're going to be dealing with. H of x, 3 times the quantity x to the fourth plus 1. I just factored out the 3 in the numerator, divided by 4x cubed plus 1. So for instance, if we start off with x not equal to plus 1, we'll be substituting 1 into h. Well, when I substitute 1 in, notice 1 plus 1 is 2, so we get 3 times 2, which is 6 for the numerator, and down in the denominator, 4 times 1 plus 1 is 5. So h of 1 is 6/5. If we decide to start with x not equal negative 1, we'll be replacing x here by negative 1. So then in that case, negative 1 to the fourth is still 1, so the numerator is still the same, 3 times 2. But negative 1 cubed is a negative 1, so now this becomes negative 4 plus 1, which is negative 3, and so we have effectively negative 3 times 2 over 3. The 3's cancel, and we're just left with negative 2. Now, in general, you'll notice that if we're doing these by hand, we're going to be getting fractions. We're putting in fractions and computing fractions. And so what's useful to do is to actually write h of x in terms of what happens with a fraction a over b. So here's what that will look like. Notice if I take x and replace it everywhere by a over b, I have 3 times the quantity a over b to the fourth, which is of course a to the fourth over b to the fourth plus 1, divided by 4 times the quantity a cubed over b cubed plus 1. And let's simplify this one by multiplying by b to the fourth over b to the fourth, and that makes the numerator simple. It just becomes 3 times a to the fourth plus b to the fourth, and the denominator is 4a cubed b plus b to the fourth. We could also factor out a b down here in the denominator. But in any case, notice once I have the h in this form, h of a over b, I'm going to be putting a fraction in and getting a fraction out, you see. And so that makes the procedure kind of run more smoothly. So in this case, we'll find if I start off with x naught equal 1, we found x1 is 6/5. You replace a everywhere by 6, b everywhere by 5, and we get the new numerator is 5,763. The new denominator is 4,945, and of course that's approximately 1.165. But in any case, you see, you could go on with this. If you're computing by hand and you have the time and energy to do it, you would now replace the a in this expression by 5,763 and replace the b everywhere by 4,945, and you'd get a tremendously long fraction, and you get better and better approximations of the root. Now let's look at what happens when we take x naught to be negative 1. Again, h of a over b, 3a to the fourth plus b to the fourth divided by b times the quantity 4a cubed plus b cubed. So now we take x naught equal to negative 1, and then we find easily that x1, the second step, is negative 2 as before. And so x2 is h of negative 2 over 1. So our b is 1 and a is negative 2. So when we calculate a to the fourth plus 1, negative 2 to the fourth is 16, plus 1 is 17, so the numerator is 3 times 17, whereas negative 2 cubed is negative 8 times 4 is negative 32, plus 1 is negative 31. So our new denominator is negative 31, and so we get as our second approximation, in this case, negative 51 over 31, which is approximately negative 1.645. Let's use Newton's method to find the fourth root of 2. Of course, that means get an approximation to the fourth root of 2. Find the approximate value of fourth root of 2 by using Newton's method to solve x to the fourth minus 2 equals 0. Start with x naught equal 1 and find x2. In other words, the function we're dealing with is the polynomial function f of x equals x to the fourth minus 2. So we begin by differentiating. F prime of x is simply 4x cubed. And so let's set h of x equal to x minus f of x over f prime of x, that's x to the fourth minus 2, divided by 4x cubed. So this is what we want to begin by simplifying in order to do our calculations. So we have h of x is x minus x to the fourth minus 2 over 4x cubed. So let's begin by getting common denominator. So we have x times 4x cubed minus the quantity x to the fourth minus 2, all divided by 4x cubed. That's equal to 4x cubed times x is 4x to the fourth minus x to the fourth minus a negative 2 is plus 2, all divided by 4x cubed. So 4x to the fourth minus x to the fourth is simply 3x to the fourth, and we end up with 3x to the fourth plus 2 divided by 4x cubed. Okay, so now, for instance, if I wanted to find out, starting with x naught equal to 1, I can easily find x1. I just compute h of 1. So h of 1 is x1, and so what will h of 1 be? 3 times 1 to the fourth plus 2 over 4 times 1 cubed, which is 3 plus 2, or simply 5/4. Now notice, again, we're getting fractions, and so it's going to be useful to look at our function h of x, which, remember, h of x is just 3x to the fourth plus 2 over 4x cubed in its simplified form. And so what I want to do is simply look at h of a over b. And so let's do that next. H of a over b then is 3 times a to the fourth over b to the fourth plus 2 divided by 4 times a cubed over b cubed. And so to simplify that, we'll multiply by b to the fourth over b to the fourth, and that gets rid of the denominator here in the numerator and the denominator here in the denominator. And so we get h of a over b has the form 3a to the fourth plus 2b to the fourth divided by 4a cubed b. So now if I want to stick with working with fractions, you see, if I put a fraction in, I get a fraction out with whole number numerator and whole number denominator. So we start off with x naught equal 1. H of 1 over 1 is 3 plus 2 over 4, which is 5/4 again. And then h of 5/4 is 3 times 5 to the fourth plus 2 times 4 to the fourth over 4 times 5 cubed times 4. And you calculate that, you get 2,387 divided by 2,000, which is approximately 1.1935. One thing you may have noticed from the geometrical picture of Newton's method is that it converges faster usually if your initial guess is nearer the root. That is, given two competing first guesses, the one that's closer to the root will generally converge faster to the root. Suppose you were really lucky and actually guessed the root. What would happen? Let's look and see. Guessing a root. Suppose f of x naught equals 0. That is, our initial guess x naught is a root, and f prime of x naught is not equal to 0. What happens to x1 in later approximations? We have to require that f prime of x naught not be equal to 0 in order that Newton's method applies. So what are we going to be doing? Well, remember, we look at the function h of x, which is x minus f of x divided by f prime of x. And we take our initial guess, put it into h of x, calculate the value, that gives us x1. We put that back into the function and keep going. So what does it mean that f of x naught equals 0? Well, notice if f of x naught equals 0, then h of x naught is simply equal to, when I put x naught in here, the numerator is 0, the denominator is non-zero, so this whole term is equal to 0, it's gone, and all I get is x naught. But h of x naught is, by definition, x1. In other words, x1 is equal to x naught. So when I go to put x1 into h, I'm really putting x naught back into h, and it just gives me x naught again. In other words, all the xn's are now equal to x naught. In effect, we've found a point which has the property that h of x equals x. X naught is a solution of the equation h of x equals x, and we call that a fixed point of the function h. And so that's what happens once you found the fixed point of the function h, then all the later approximations are stable. They never change. Well, in certain circumstances, Newton's method will not work at all. That is, it may be possible that there are 2 points on the curve such that if you happen to make the wrong guess, this leads to a cycling. You start off x naught equal x1, then x1 goes back to x naught, then x naught back to x1, and back and forth, and you don't get anywhere. Let's look at an example to see how this can happen. Show that if h is greater than 0, applying Newton's method to the function f of x equals square root x for x greater than or equal to 0 and square root negative x for x less than 0 leads to x1 equal negative h if x naught equal h, and to x1 equal h if x naught equals negative h. Now we can simplify this by noticing that this function here is the square root of the absolute value of x. After all, the absolute value of x is x for x greater than or equal to 0, and the absolute value of x is negative x for x less than 0. So equivalently then, we can say that our problem is with f of x equal the square root of absolute value of x, and we show Newton's method applied to any x naught not 0 gives x1 equal to the negative of that starting value. So that would mean x2 is the negative of x1, which of course is the negative of x naught, which is back to x naught, and so you'll be cycling. In effect, x2 equals x naught, x3 equals x1, x4 equals x naught, and so forth. You never get anywhere. Well, with the problem in this form, notice when we go to differentiate the function f of x, we're faced with the problem of using the chain rule and differentiating absolute value of x. So how do we differentiate y equals the absolute value of x? The way to go is to use the fact that absolute value of x is simply the square root of x squared with the chain rule. Okay, so now what I want to do then is begin by differentiating the function. So the function we have to deal with is f of x equals square root absolute value of x, which is of course the square root of the square root of x squared. The square root of the square root is the fourth root, and so we can write this as x squared raised to the 1/4 power. So f prime of x is equal to 1/4 x squared to the 1/4 minus 1, which is negative 3/4, times the derivative of what's inside, which is simply 2x. Well, notice we can cancel a 2 with a 4, and so down in the denominator we end up with just a 2. Let's put x squared to the negative 3/4, write it down in the denominator. It becomes x squared to the 3/4, which is x squared to the 1/2 to the 3/2, and in the numerator we still have our x. Notice x squared to the 1/2 is absolute value of x, so we end up with x divided by 2 absolute value of x raised to the 3/2 power. So to form our function h of x that we plug our initial guess into and then recompute its values by plugging values back into the function, h of x, remember, is x minus f of x divided by f prime of x, which is now x minus square root absolute value of x divided by the quantity x over 2 absolute x to the 3/2. So that's what we want to simplify. So let's look at that one then. H of x is equal to x minus square root of absolute value of x divided by the quantity x over 2 absolute value of x to the 3/2 power. Now notice we have something in the denominator of the denominator, so it comes up top. This is the same as x minus 2 absolute x to the 3/2 multiplied by the square root of absolute value of x all over x. So coming down one more line, x minus 2 absolute value x to the 3/2. Square root of absolute value of x is absolute value of x to the 1/2, all divided by x. And now absolute x to the 3/2 times absolute x to the 1/2 is absolute x to the 4/2, which is absolute x squared. So we have negative 2 absolute x squared divided by x. Well, absolute value of x squared is the same as x squared. So that's x minus 2x squared over x. Now we can cancel x with x squared. We end up with x minus 2x, and finally negative x. And so there you see very clearly that our iteration procedure using Newton's method, we start with x, we end up with negative x, and that's it. Well, we can use Newton's method to find roots of polynomials to very high accuracy. Let's try one. Use the intermediate value theorem to show f of x equal x cubed plus 2x minus 4 has a root between x equal 1 and x equal 2. Then find the root to 5 decimal places. At this time, why don't you pause the video and try this problem on your own. Well, let's begin by considering the intermediate value theorem. It tells us that if a function which is continuous on an interval assumes 2 values, then it must assume all the values between. So for instance, here our function f of x equal x cubed plus 2x minus 4 being a polynomial is differentiable even and therefore continuous. And so as far as the closed interval from 1 to 2 is concerned, let's look at the value at 1 and the value at 2 and see what we get. At 1, we have 1 plus 2 minus 4 is negative 1. So f of 1 is negative 1. Now let's plug in 2. 2 cubed is 8. And then here we have 2 times 2 is 4 minus 4. They cancel each other, so we're just left with the 8. F of 2 equals 8. So on the interval from 1 to 2, which we're going to look at, here at the left endpoint, the value is negative 1. At the right endpoint, 2, the value is 8. So in that interval, the function has to assume every value between negative 1 and 8. In particular, since 0 is between negative 1 and 8, this function has to assume the value 0 in that interval. In other words, we're guaranteed by the intermediate value theorem that there is a root in that interval. That means what we want to do is look at the graph of the function around this interval just to get a good guess as where we would start using Newton's method. Now to do that, what we've done is use our graphing techniques. We write down the function. It's f of x equal x cubed plus 2x minus 4. We compute the derivative. F prime of x is 3x squared plus 2. And the second derivative, f double prime of x, is 6x. Notice from the second derivative, we can tell this function is concave up for positive x and concave down for negative x. So its inflection point is at x equals 0. And at x equals 0, the value of the function is negative 4. So right down here at negative 4 is where we cross the x-axis, and that's our inflection point. If I put x equals 0 into the derivative, I get simply 2, and so the slope where we cross the y-axis is 2. But notice, once we've gotten here to x equal 1, the slope is 3 plus 2, which is 5. That's quite a bit steeper. On the other hand, over here at 2, the slope is 2 squared is 4 times 3 is 12 plus 2 is 14. So here this curve is really zooming up. On the other hand, if I draw a straight line through the 2 points on the graph that we've computed, 1 comma negative 1 and 2 comma 8, that straight line obviously has slope 9 because you go over 1 and we go from height negative 1 all the way up to 8. Slope 9 is less than 14 but bigger than 5, and so this curve is bowing out here, but it's passing through both these 2 points, and so consequently the root of this cubic polynomial has to be to the right of where the straight line crosses the x-axis. Notice it obviously crosses at x naught equal 10/9, which I'm going to take for my initial guess. You can see that's going to probably get me very close to the root just to start with, and that's going to help me get 5 decimal place accuracy. Now remember, when using Newton's method, what you're doing is you're forming a function, essentially x minus f of x divided by f prime of x. We're taking our initial value, putting it in for x, computing a value, taking the result, putting it back in, and so on and so forth. How are we ever going to know that we're getting 5 decimal place accuracy? Now, one of the things that's often done with Newton's method is you would just go out until the first 5 decimal places quit changing, and then most people would assume that that's the answer to 5 decimal places. Actually, there's no guarantee, no matter how many steps you go, that you might not hit some wild oscillation point in the graph causing the procedure to start giving you much greater variation in the values. In order to actually be guaranteed that you're getting close, you'd have to go through the analysis of the first and second derivatives that tells you how to tell how close you're getting to the root in terms of the square of the difference between a previous guess and the real root. Now, if you carry this analysis out that's suggested in your textbook in the case where the x naught is a half, you know right away that the root, no matter where it is in the interval from 1 to 2, is at most distance 1/2 from the center of that interval, and 1/2 squared is 1/4. And so with that estimate and using the first and second derivatives here, for instance, we see the second derivative here on this interval can be at most, 6 times 2 is 12, and the first derivative is at least 2 and at most 14 throughout the interval. So making these estimates, it's possible to see that within 5 steps, starting at 1/2, we will definitely get to 5 decimal place accuracy. But without going through all that, let's start right here at 10/9. That should get to the root even faster. And we'll just look to see that, in fact, once we've done that, we get very soon that the first 5 decimal places stay the same. So we're going to begin by computing x minus f of x over f prime of x. And I'm going to call that h of x for simplicity. So h of x is x minus f of x over f prime of x, and so that's x minus our function x cubed plus 2x minus 4 divided by its derivative, which is 3x squared plus 2. And let's begin by simplifying that. So we get x times the quantity 3x squared plus 2 minus the quantity x cubed plus 2x minus 4, all divided by the quantity 3x squared plus 2. So let's simplify. We'll distribute the x through the first term. We get 3x cubed plus 2x. Let's distribute the negative sign through the second term. Negative x cubed, negative 2x, and a negative 4 becomes a plus 4, all divided by 3x squared plus 2. So now notice the x terms cancel. 3x cubed minus x cubed is simply a 2x cubed. So we have 2x cubed plus 4, all divided by 3x squared plus 2. So a little bit of algebra here is going to simplify the calculations quite a bit. Now, of course, we'll be dealing with fractions a lot when we do this. And so consequently, what I'm going to do is look at this expression, h of x equal 2x cubed plus 4 divided by 3x squared plus 2, and I'm going to take h of a over b and simplify it by multiplying through by b cubed over b cubed. And so that results in 2a cubed plus 4b cubed divided by the quantity 3a squared b plus 2b cubed. So now what we'll find is when we start with our x naught equal 10/9, then x1 is 4,916 over 4,158 just by putting 10 in for a everywhere and replacing b by 9. And that's approximately 1.182299. So now we'll replace a everywhere by 4,916 in this expression and replace b everywhere by 4,158. And when you do that, even with your calculator, you'll get about a 20-digit number, and you can calculate that pretty easily. It comes out to 1.179513. Notice 2 5 decimal places, we're getting 1.17951. When we do this again, putting in x2 into h of x, you find h of x is 1.179509, which still rounds off to 1.17951, 2 5 decimal places. In fact, when you compute x4, you get this same number again to 6 decimal places, and likewise for x5. Well, since we know we only have to go 5 steps to get 5 decimal place accuracy, if you accept that I did the analysis, then that means that we're guaranteed right here, in fact, that we hit 5 decimal place accuracy actually on our second step. Of course, the main reason we got there so fast was because we started with x0 being 10/9 that we got by looking at the graph. Okay, well, we've worked some problems using Newton's method. Remember, when dealing with Newton's method, if you actually have to calculate by hand, compute the actual x minus f of x over f prime of x and simplify it, and then replace the x by a over b and simplify that so that you have a procedure for taking fractions, putting them in, and getting out fractions. You can calculate that much more rapidly and much more accurately. Now, another thing to keep in mind is Newton's method is very sensitive to how close your initial guess is to the root. When you're dealing with polynomials where you can make reasonable graph sketches using your graphing techniques, using the first and second derivatives, keep in mind how concavity and the increasing and decreasing relate to the graph. You can often get a much quicker estimate as to where the initial guess should be.